All right. So today, the focus of today is the logic synthesis. So logic synthesis, put it simply, it's just like the input is a Verilog RTL source program, and the output is the gate netlist. So in this picture, okay, in this picture, I think there was a confusion in the previous class, in the class on Thursday. The synthesis, you see that is like until here. Thus, the output of the synthesis is the gate netlist. So the gate netlist here, to be clear, it's just a file describing the cells to be used and the connection between those cells. That's all. To get to the photomask pattern here, we need to go through the physical design to get to this, and then we go this. So synthesis is from here back. Okay, so don't be confused by this picture that show everything. You just like the thing is a logic synthesis is the output is the gate netlist, the file. So I think there's the lines. This means that the designer has to write all the logic blocks necessary to make them work properly themselves. They just want to like because you write code, right? So like a C code, like a C sharp or like Python or whatever, like a Java, and then those code will be run on the computer. It's different from here. You write code too, but that's like RTL code. But this RTL code or like a HDL, high like a hardware language code, right? Hardware description language code. So you write that the outcome of the RTL code it will be like this. It will be on the silicon. So this slide just to show you that it's different from a software application. It's also code, but this code is not converted to binary to be run on the computer. This code will be converted to a file, and then finally will be like turn out converted to the mask pattern. That's this slide that is to make that clear. So it try to make it clear, but maybe it's like on the way it might confuse you because of this picture. I think the student of the previous class was confusing because of it. So I try to make sure that okay, forget about the right. Okay, this one forget about it. Just like a logic synthesis, only this part on the left. So let me, because I think I remember that like all right, let's just make like okay. So yeah, here it just like show the difference between the software code versus the RTL code, right? So from the left, this one is C source code, A equal to B plus C, compiler into like that. Execute. Actually, this one is assembly code. This one's assembly code. So it will be like a transfer and then converted to really binary. This one is still not binary, right? So I think this one need to be like convert to again like a binary, and then it will be like run on the CPU. So it needs the CPU to run it. The RTL source code here, it will be synthesized into again, I think this, and the final product will be the mask to the silicon. So the final product is the silicon wafer, or is the chip. Now, okay, let me like clear up this one so that I think I can start over here. Yes, okay. All right. So you see that again, this picture show very clearly on the left is the input to the logic synthesis tool. On the right is the outcome is the main thing is a gate netlist. This one is the text file. This one is a text file. right? And along with that, you have the synthesis report to like a report for you how many cells are used, what kind of cells are used, the clock skew, the whatever. Yeah, I think it's the how much that power is used, what is the total area, what is the capacitance, wire length, and so on. Whatever. I think you'll have a synthesis report here. But this one is just for report so that we check the synthesis result. It like this one is a report, right? You know what is it? So the report is used to check the thing. The key thing is that this one will be used to go to the PD, physical design. So go to the physical design and then finally turn that out to be turn that over to be a mask. So again, I repeat, the final outcome of the logic synthesis tool is the gate netlist. It's a text file describing the cells to be used and the connection between the cells. The process inside the logic synthesis, right? You have an interpretation of the RTL, you have a logic optimization and library mapping. So in these three things, it will be explained, I think, in my like extra slide. I will explain that like further. So the input, first of all, you have an RTL description. That's like everybody knows it. Now, when you write the code, so usually always, right? Not usually, always there's a target frequency. The frequency need to be targeted at a certain number. So when you do that, let's say like a 1 gigahertz, 2 gigahertz, 500 megahertz, and so on. So that is defined like the first thing to define is a clock period here. That's the first thing. Now the second thing is the timing and drivability at the core boundary, which is like the IO condition. So you know that like the IO condition is important because you have if it depends on, let's say like you have the chip, right? And then like you design a block inside the chip. So let's say you have a two block talk to each other. So this one go that, this one go that. So in this, it's a bus or like a multiple like a line here, multiple signal here. So that means let's say if I write, I just magnify it. One is like the input will be like this, right? So there will be like so it go like that. So we need to like if you design the block here, you design this block, you need to know the condition at this like boundary, because go inside here you have a logic here and then it go to the flop here. So you need to know that like in this one, right? In this one you have a block here going here. In this one you have block here going here, and then you have this. The rectangle here is the flop. So the frequency is defined by the delay between these two flops, which is you need to know what is the condition like at the boundary here, so that you know, okay, even I have the frequency like let's say a frequency is 1 nanosecond. Sorry, the period is 1 nanosecond, which is 1 gigahertz. The 1 nanosecond here need to be distributed from here until here, right? So which is you need to know like okay, this part of the block A talk to the block B. This part take let's say like 500 picosecond, which means you put like the condition here is 0.5 nanosecond, right? That means that in fact it come to like then your block here has only 500 picosecond to like achieve, which means like instead of having 1 nanosecond totally for this one, right? Now you have only 500 picosecond, but you know 500 because there's like the budgeting here. You know that like the boundary condition here is 500, but if the other guy like it's a very critical and it cannot 500 picosecond on the lab is not enough. They require to have a 700 picosecond. Then they will put here 700 picosecond. Then inside it's become only like 300 picosecond. Then you have to make your portion here to be as fast as like the delay is only 300 picosecond, not 700 picosecond. right? That's called like that's one example of the timing and the reliability at the core boundary. So that's the timing at this. That's one thing you have to. They have to give you what you design. You just design a block here, right? You don't design the whole thing. Design the whole thing. Let's put it away. That's different. But that's called like SOC. But you just design one block. So in the SOC or in the chip, there's a multiple blocks. So there will be like the boundary condition, or they call that like an interface condition, interface or IO. Then you have to like specify that. The reason you have to specify that so that like the logic synthesis tool know that, oh, okay, inside here, right? If I put that inside here like this, the inside here will have the total delay of 1 nanosecond, but the portion here will be only 300 or 500 picosecond, depends on the boundary condition. Another thing is about the operation condition. That one is the long one. I think okay. Then let me explain. This one take a little bit of time. Okay. In a chip, okay, it's the operation condition here is called like a P, V, and T. PVT means process, voltage, and temperature. Process means it's like this one is a transistor process. This is transistor process. V is a voltage, is like the chip voltage, the voltage of the applied to the chip. And here's the temperature, which is the temperature, ambient temperature. So the operation condition here, we have to specify that. Why do we have to specify that for the logic synthesis tool? The reason is in the chip, here, let's say you have a chip like this. The transistor, you know, when they produce a chip, nothing is uniform, right? In life, nothing is uniform either. People were born, right, with different things, like poor or rich or poor, or like good or bad, or whatever is character is different, and so on. So everything is different. The same thing is in the chip. So because of the process, like it is not like even, right? The transistor here and the transistor here and here, everywhere they are not the same. So if we put like if you, I think if you learn about, you study about the statistic, then you know, and probability and statistic, you know that the distribution, the normal distribution for everything, when you have like enough patterns, right, enough samples, is like this. So, oops, what is? So the thing is that you have so its distribution like that's the normal distribution, which is like most of the transistor here will fall into this, right? Most of them will do this. This is 1 sigma. Actually, 1 sigma is inside here. Until 3 sigma is like this. 3 sigma go down out here. That's the 3 sigma. I think it's about 97% or 99%. I think 97%. The 3% left will be like at here. So most of the, and they call the middle here is a typical, and this one is a weak, and this one is a strong. What they call weak and strong. This one is in terms of current, which is they can do that as in terms of like mobility, or in terms of because you know the current run through the transistor is proportional to the mobility, right? In proportional to the width. So okay, so that's width or current. So with that, the same transistor with the same width, but in real life, the width will be like go from here to here. The width that design in the middle is a typical, will be most of the like transistor here will have the width in between here in this area. but there will be the transistor with the width like almost like at the end here as the maximum, which is like the max here. Here's the max. Max current means strong, right? They call that strong because it's a strong process, mean like you have a strong current or like a strong performance. The other one, you have when you have the width is small, you have a weaker current, which is you have a weak or you have a So that means like and then they have they have a distribution which is let's say I put here is let's say like a 1 milliamp. Then this one will be or like for the width. Let me see. Let me put that this way. What caused the current change is just the width, the transistor width. So let's say here I have the width here is let's say it's about like 10. Let's say I have a 40 nanometer, but the spec is a 40 nanometer. Is supposed to be typical, but in the transistor here you have that vary by let's say like 10%. You have that like here is a 42, and here's a 38. So the variation is about 10%, right? So that means that when you have that, which means you have a transistor is somehow the performance are different. That's why you have the P here. So, but you see that it changed from here to here. The range is changed from weak to strong. But you cannot put every value here into like give that to the logic synthesis tool. It cannot handle that big data. So the simple way is they just make it like a take three like value. The first value is typical, and the second value is a weak and strong. They put that into 3 values, and then they give that to the logic synthesis tool, which is now we have here transistor here. You have a 3 value to here. It's like a weak, typical, strong. So that like because when you have okay, let me go further before I come back to like why the logic synthesis need all of these things. The second is the voltage. The voltage is applied to the chip, right? Applied to the chip. So the voltage go to it is provided to the transistor through the power grid, the power PG, power grid. The power grid is a system of metal wire, thick metal wire. So it go like this. And you have the voltage, the power supply, right? Go to here as a certain pin. Let's say one here, one here, one here, and one here. So because of it, it go like this and need to like use the power grid to distribute the power to each transistor, right? And you can see that the voltage here is not the same as voltage here, right? Even you cannot, that means like the voltage at each point in this won't be the same as the other. First of all, because of distribution. Second of all, because of the metal wire here are not uniform either. What you see that the process of producing the chip is like you have let's say like when you draw that in the mask like this, right? This one the metal wire so that to connect between like this go to this, right? This is a wire, but you draw that beautifully, very straight. But in the when it used it used the lithography to like make a chip, then this one will become like something like that. So you have like uneven here, and if you have because of it, right? Some like that, some go like this. Because of it, the drawing is the same, but it will be different. Each won't have the same value. Because of that, that's you have the current go into here will be different, right? So that means like the voltage inside here will be different. So what come out now? What is the consequence? Let's see, you have the voltage of the regulator. Here's a regulator. The output of that is a 1 volt, right? And then from here, they will connect to here, and then connect to here and here, right? And here. So assuming that like those y here, those y to here is the same. So that means the voltage at the input here, in here, and here, these are A, B, C, D. Those that at those input, the voltage is the same, right? So let's assume that. Even that, the voltage inside here is not the same. So because you have so many things, the distribution will follow the same shape like that. So because of it, you have a mean, max, and typical. Because of it, you have V here, you also have like a mean, max, and typical. That's one thing. Now, there's another thing. When there's another thing. When you have the circuit function, the circuit will function in different modes, right? And different, for example, like when it take the voltage, when it take the picture, the camera will function along with the image processor. So these two parts will be turned on. However, the other part, like the GPU, will be turned off because it's not needed, right? So which is like, and then like, let's say the image processing is very high performance. It run like very high like performance. So it need very like, it need the biggest voltage. So that like, then it need, let's say they need 1 volt. But now the other one is like the block. There's a block like a small block to control the turn on and off of the like to control the switching between the block, right? Let's say like there will be a control block to turn on the GPU, to turn off the GPU, to turn on the like image processor, to turn off the image processor, and so on. So that control thing is a power unit. That one doesn't need to be at the high voltage because it doesn't need to function at the high frequency, right? Because of it, they don't need to be like they don't need to be high frequency. Then they just run that at for example 0.6 volt, right? And then there's also like some circuit run at like 0.8 volt. So the bottom line is because of different functionality and to save the power, right? They will have a different voltage to meet the requirement. Because of it, you have a multiple voltage. So that means that you have the V here. It can be like it vary for two things. First, it will depend. You have the main voltage, like the typical voltage for each purpose, for each mode. Then for each voltage like that, let's say you have this one is 1 volt here. What is this? Is what? Okay. Yeah, okay. So with each voltage, let's say like a, okay, yeah. Yeah. With each voltage, let's say I put this one is 1 volt. Then there, because of this one, there will be the variation. Then it can be between like 1.05 and 0.95. So that means that for each voltage, for each like a typical voltage for each mode, there will be like the variation from min to max. So which is you have a voltage here, there will be like some 10 or 20 voltage here. For like a different purpose, and each voltage will have the minimum, maximum, and typical. So the combination of all the voltage here can be like about like 30 easily. 30, yeah, it's about that. Then you have a temperature. Temperature, you see that when the circuit, let's say like the circuit function, it need to be to be able to operate everywhere from the Arctic to the like African country which is hot, right? The desert. So which is you have to like the frequency. Sorry, The temperature can vary from like a minus 40 degrees C and go to like they call that like 25 C is a typical. 25 C is typical. That's what we got like in the air condition. And then it go to 155 degrees C. That's like a military grade. In the commercial, it will be like a 125. But military, they require like 155, and it's here's a minus 55. That's for military. These two things. Okay, so which means like you have a temperature vary. It need to like the chip need to work in every condition. So that's why you have a minus 40, 25, and 155. There's also different temperature. For example, again, you have the block here and the block here. There's two things. One, they don't, let's say like they are not turned on at the same time because they are not needed, right? So when this one turn on, it will generate heat, so it will be hotter. The other one is not turned on because it's not needed, it's not operating, so it's cooler, right? Even when both of them are turned on, it depends on the frequency of each. So the temperature of this block will be different. So when they do the infrared spectrum to see like what is the temperature in here, there will be something like that. So the spectrum will be like very different. Like they show the temperature of on the chip will be like in this corner maybe it's cold, but in the middle because there's no like it cannot like the heat cannot escape, so it's maybe hottest, but it's not sure it's hottest. It depends on the block it runs or not, and it runs at the high frequency or not. It depends on a lot of things. So that means that it can happen anywhere, which is the hotspot can be in the middle, can be like at the outside, whatever, and then it won't be even. So there's a three things. First of all, you have a three like main value actually, not three main value. It depends on the mode and the purpose too. You have a minus 40, 0, 25, 75, 125, 155. Those are the main value for the temperature. So with that means the T here you have about like about 10 value. If you have all these 10, right? You combine that, process the 3, this one is 30, this one 10, you have a total is 10 by 30 is 300, with 3 is 900. So total will be 900 or even more. The current, what we are doing right now, like to check the design, right? So you check the design at about 200 to 300 corner operating system operation condition. So that's really a lot and a lot of work. Like so the logic synthesis, when you run like in the old days, it run only at about like 20, 30 corners. Corners mean like operation condition, but the practical or like the usual work we use in our industry is a corner. So we have about like 20, 30 corners in the past, 20, 30 years ago. Nowadays it's between 200 to 300 or even more. You see that here, I just calculate and show you like it's easily 900, but it's not that 900. We don't use 900 because it's too many, right? So we just like remove whatever we think is not real, right? There will be something like some. So when you do that, okay, we say that the 75 here is only in a certain scenario, so we just cut off a lot of things for the 75. The 125 is for military, so we just like cut it off. We just do that if we need the product to be used in military. Minus 55, same thing. So I think we cut off the corner. You remember there's the terminology in English that cut the corner, right? Cut the corner means means cut cost. So here the same thing. We cut that so that you have a less thing to run. What like instead of running on like take into account of 900 corners, that means you have to like run the logic synthesis here meet the requirement of that 900 corners, you meet now, actually not really, but only 300 corners. It's a enormous like time to do that. It's a lot. But I just explained to you, because when you do that, you will see like the terminology PVT. Remember that one is used a lot. Process, voltage, and temperature. Process is only for transistor. Voltage and temperature, these two, you know, what is the effect? What does the effect? It affect both the transistor and actually there's one more thing. Voltage affect the transistor. Temperature also affect the transistor. So PVT affect all of them. Now what affect the wire? That is the temperature and the process. But now affect the wire is a P and T. But the P here is a process. Here is a process for the wire, which is like you have the width, right? The width like that is a typical, but it might be that large or maybe that small in the middle. So if this one P here is also process, but process for like the wire. Because when you have when the width vary, you have the wire resistance vary, right? Also the wire gap vary, whatever the wire varies. When the temperature varies, which is you have a high and low, then the resistance will be like a change, right? So that means that you have that too. So the PVT here is for the cell library, and the PT here is for the middle, for the middle wires. The third one important thing is the library information to provide to the logic synthesis. So which is you have a cell list and cell information. Synthesis tool need the cell list so that it know what cell to map to, right? It just like convert from the RTL and then it will use the cell to map to. That's first. The second is that it needs the cell information like a function delay size. Function delay size, function, you know why, right? It need to be like the cell list. So each cell has a function. It's not by the name only. There will be a field in the cell, like information about like what function does this cell like implement, like a NAND, a NOR, a SAW, exclusive or the like exclusive NOR, and so on. So that it will like map. Okay, I will explain that into that and during the synthesis the process. And then delay size, so that like remember the delay, so that you know like when you map into, when you use the NAND, so there's like 10 or 20 types of NANDs, and each of them, because of the speed, if the use it increase the width, right? So the delay will be different. But the synthesis tool doesn't need to know the width information. They just need to know about timing, because that's what they use. So what they need about like actually there's a couple things too. You have a delay size and also power. Here's a power too, because that they need here to like meet the requirement about PPAS, right? So they need delay so that they can meet the requirement about performance. So let's say like then they need the size. The size means that the size of the cell, not the width size. So the size of cell, so that they can calculate the total area. That's come with like to meet the requirement for the area. And they need the power. So the power information here come into like a two table. One is a leakage, and one is a internal, which is the short circuit power. Short circuit power. So it will show you like this cell has how much leakage, and then along with that you will have the short circuit power, which is you have with the input slew and with the output load, right? And what is the short circuit power? Based on that, the tool can calculate what is the power that the cells consume. Then they can balance when they synthesize to meet the requirement for the performance. they will decide to use the cell with less power or more power, right? Now, for example, like okay, this part is critical, so they have to use the high-speed cell regardless of the power area. But now let's say this part, I think they have another path. That path has let's say only 50% of the delay of the period. The clock period, let's say like 1 nanosecond, and this part delays is only 500 picosecond, right? So it has an enormous room. So that means that I don't need to use a high-speed cell. I just use the smaller cell. So because of it, I can calculate, okay, I will, but it's not like you go all down all the way. You have to still meet 500 because you need to meet that 1 nanosecond, right? Delay 500, you can increase that. You can increase that delay to 1 nanosecond only. You cannot increase that to like a 1.2 or 1.3, which is you don't have the freedom to just use the smallest cell, because the smallest cell is like the one consume the least power and has the minimum area, right? So which is, I think there's a sweet spot. The first thing is to meet, okay, a target is the performance. As long as you meet the performance, you just reduce the power and reduce the area as long as it meets performance. That's why the library information provided by the foundry, it will have to provide you the delay size and power, and it has to provide the function variable too, so that you know which one to map to, right? So with that, the tool will do the first of all, interpret the RTL, convert that to the Boolean, and then do the logic optimization. After that, they will do the mapping, and after mapping, you will have the get netlist file. This is well, yeah, I think this one is just to show you an example, right? So it's straightforward. So you can see that it's go from the left to the right with the get that, but remember until here is still the get netlist. I think I hate this one. It's just confused. So, yes, no mask pattern yet. It's just that it's just like it's just the cells. Yeah, it's just the cells and the connection. No mask. And in this, I think just to illustrate, to demonstrate that how it maps from the RTL to the on the right is the get netlist. You see that the get netlist, because you see the description of here is the cells, right? And you have a connection is D here, connection to here. So this the output of this cell instance 1 connect to the A1 of the instance 4. That's called the net. D is called the net name. So I think then it's all like this. The RTL, the output, which is the RTL, the Verilog netlist, has all the thing. The description is like this. That's the outcome, and it can be optimized to have the minimum or have the best performance and so on, depends on the purpose. Here, I think it's synthesis here. All kind of this one is all synthesis. But the first one is just to convert. This one is just a convert from RTL to Boolean. Simple one. And the next one is optimization, so that you have that, and you search the optimize to have now you have only 3 cells, right? This one you have 1, 2, 3, 4, 5. Optimize, you have 3 cells. That's how synthesis works. It needs to convert the RTL description into a Boolean system. From there, it will work on it and finally optimize it, and then finally output the best version of that, which is only 3 cells here. Cell-based design, and then this one again, I think you have a net list, right? And this one is a layout like this. This one is supposed to be like implemented on the layout on the chip, but this process to have this one like implemented is in the PD, not in the logic synthesis. At this step, logic synthesis, again I repeat, you have only the text file describing the cells and the connection between them. How it will be placed and connect, and I do what like implemented on the layout is the work of the PD. This okay, just ignore it. I think it's I will explain that in the other one. Get level design and verification. Verification. All right. So in this one, I think I change a little bit. So there's a 3 level of 3 type of information depends on the step. So the first one is they call that like the front end, the back end, and the layout library. The layout library or like the foundry library, right? So this one I think is like for the photo mask, so it goes to the foundry. And then the backend library is for place and route. Front end means for the synthesis. This one for the synthesis. Okay, so you have the library. Library will have 3 type of library: front end library, backend library, and layout library. So what you have to deal with right now is a front end library for the synthesis. It has like I explained here. Here, it has the function, delay, size, and power, 3 things. So that's like here to choose about delay and drivability, which is the size, and then you have a power here too. The backend library is the left file format. So this one is used by the place and route tool. So we will go there at the end of the class at the program, which is during the layout design or physical design in the week 11 and 12. Layout library, you don't need to know that. This one is to go to like the foundry. So you can see that, okay, the green here is a layout rule minimum and so on, right? This thing, but that's why I think it's the backend library 5 and 3. So the layout rule here actually is not really like in the it's not only in the I think the fine for this one. I think yeah. The blue color is a backend library. So you look at here, it's only 3, right? But actually it's a 3 and 5 because the layout rule is also like provided for the backend too. The backend library need to have the layout rule. Sorry, need to have the layout rule. Yeah, it need to have the layout rule so that it can do the place and route correctly. And the layout, then the third one, layout library, it need to have a number 5, number 4, so that it can like do the math. Why rule? Okay, okay. I think I'm sorry. I think that this one is very confusing. So let me like correct it. The same layout rule, wiring rule here is the same. Minimum distance between cell, minimum pitch, multivia, and so on. This thing is about like the layout rule. Okay, so let's say it's all number 5, no number 6. All right, so I think with that, let's see. I said this one is far array, right? So which is whatever is nice far array, we don't care. The backend is what we need for the PD. This one for PD, and this one is the front end, which is this one is a synthesis. Basically, front end has a synthesis, is also the RTL. But usually the front end library is like to make it simple. Okay, to make it simple, front end library is used by the synthesis, which is I think delay, drivability, area, and area. Area and power. So this one is just that. This one not about the design rule. So the design rule, you have the width, the middle wire need to have a minimum width and minimum spacing. The reason for that simple. As I said, the width of the Y when you draw this, or like when the tool draws this way, it looks very beautiful, right? It's just a straight and uniform. But because of the unevenness in the technology of the photomask, when you go to the chip, it can be like this. Like this. So it can be open, because if you have the width is too small, then it can be open. If you have then that's open, right? Now you have, if the spacing between these two Y is too small, then you have like this. These two Y supposed to be like that beautifully, but because of the unevenness, like the not perfect lithography, this one can be go this, and it can be touched, right? If it touched, it means short, which is like you have like let's say like this, now go here, and this other one, another one go like this, and because of this short here, this is short here actually, then it might like short here. You see that? Now you have the contention bus, right? This one is touched like that, circuit fail, or like you have this, then circuit fail, or like you have like this net will have like a undeterministic value. So because of it, they need to have a spacing rule, which is you cannot draw two Y next to each other too narrow, too close to each other. It need to be like at a certain distance minimum, and so on. So there will be like a rule like that. So that's like a design rule. This, I think these are the same. The similar, not much to say. Now, I think this one is functional simulation, which is okay, this one I just ignore that. I think it's not really, yeah. And then this one is the get level verification by using functional simulation. So that's one is one you have in the lab to verify, right? When you verify, which means you just like apply the event occur, you apply the text vector and you measure the output to see like if the output is as you expected. That's what the functional simulation is doing. So the simulation is always cumbersome, and then to process that, usually you dump out, and then you dump out with, I think there's a text format for the output, and you have to write script to check it, or you have to write a program to check it. Usually we don't look at the waveform to check just for the critical net, but for the whole like checking a lot, we have to use a script, or like we write the program to check it, so that we can check like 1,000 or like 100,000 of net, or like output, and so on. Now it's like the equivalent equivalence check. So you have that for the conformal GXL formality is the tool, right? So this one is the way that like the equivalence check is one kind of is a one component of the conformal verification. So it tests the content of the network against the model, a reference model, without using simulation. So yeah, this one I think I explained to you before already. Floor planning, I'm going to set and talk about SDA. Now there's another thing is a timing verification by SDA and DTA. So SDA, usually I think the work like verification for the timing like SDA, we just use like SDA timing analysis, so that we can like we use that some kind of like verification, but we don't really use that term, that terminology verification. We use the SDA tool to check against the target. So it's really like to make sure that our design meet the performance requirement. That's the main thing. And also like nowadays we are not only the timing, but with the power too. So this is 2P and A because they report there's SDA, they call that static timing analysis, right? But the tool is like include also like you have the prime time, and you have the PTPS, like a prime time power, which is like to measure the power too. And that's the tools from Synopsys. So actually the SDA is a static timing analysis. It's like the static one, so it doesn't use the simulation, so it will be faster. However, faster is to take time. If you look at the number of conditions it has to check and to like to analyze, right? 300 condition, we have to run that in parallel, because if we run like sequentially, it never be able to finish. Like one example for you to be able to imagine how complicated and how long the run can be. We run the SDA for a design about 2 million instances, which is about I think 10 million transistor. Is a 10 no, more than that. 2 million is about 20 million transistor. Is that right? No, it's more than that, because one instance is maybe is more than 4 gate, 4 transistor is not a NAND. The terminology is this: 1 gate, when they said that the design of 10 gates, that gates mean like 1 gate is equivalent to like a 1 NAND, which is a 4 transistor. But when we talk about like an instance, the instance can be a NAND, or can be a NOR, can be like a MUX, can be a AOI, like a AND or an inverter. So it can be a lot of things. So that's why I said that 2 million instances is not 10 million transistor. It's about it's kind of okay. It's got a big number, and even that it take about like we need to run on about like if we have a 300 corner, then we have to run in 300 like a machine, and it take about like 4 to 8 hours to finish, right? That's in parallel. If you run that in constant like sequentially, it will take like months, right? It will take months. So which is like that's that's because of the prime time, the SCA, it check every node, it run like the calculation of that, and then like okay, whatever, it runs a very long time. So for now, I think for the purpose in like the lab, you run that quickly, but the real life is like it's very long. this example is the critical. You need to know how to calculate the LAT, which is the latest arrival time. So let me like redo it. Let me okay. This one is okay, so I can just move this there. There. One thing I have to remind you is that to emphasize is the latest arrival time. It can be at the input and it can be the output, right? So this one, if the output, usually I think we, output or input. So here, I think in the picture here is a little bit confusing because you see that like blue italic is a gate delay, right? Gate delay actually is not really gate delay because you have like, let's say 24 and 21. What does that mean? 24 here means the delay from the input A to the output of the cell N2, right? So that means the timing out from here to here. And 21 is from like this one, from the input N2 to this. So that's why like I said like a 24, 21 here is like you have to put that, yeah, maybe closer to the input rather than like put that in on the Y, on the connection. So with that, the way of calculating the LAT, which is the latest arrival time at this one, right? What is the arrival time here? LAT. So that's like if you have a okay, this one. Okay. So you have this one is sum is this. This one is easy. Max is a max D1, D2. But the thing is like you have a go from, if you have a two input go here and output here, right? So the max is like, because the you will have the arrival time here. Arrival time. This one will be the you take like the input time, arrival time here plus the timing down here. How much here, and you sum it up, and then you sum like I think is I have to make a bigger, yeah, I have to make a bigger one. Let's say this one. So the arrival time here is, let's say like 20. Arrival time, sorry. Arrival this one's 20. Here's 25. From here to here, this delay, let's say like 10. But from here to here, this delay is like 20, right? So what is the LAT here? It will be the max of 2, right? 20 plus 20. That's 1. This part is I have a 20 to 20. This part have a 25 plus 10. So which is 40, which is to go from here to here. This one is the part of the to go to. So that means this one is 40, right? So that's how I think the same thing here. So I think the idea is, I think this one is similar to the way that you calculate the for the graph with the longest part, right? If you I think I don't know if you take the class of algorithm, it must have the way to like the algorithm to calculate this. So, now this one is not that simple. Okay, if the timing doesn't meet requirement, replace cell and reroute wiring for better result. This one is simple, but I tell you one thing so you can imagine how complicated it is for when the design or the timing doesn't meet requirement. Usually, when you have the synthesis is done, you have the netlist. Then after that, you go through the PD. The PD will take about like 1 or 2 months, and then you take like about like 1 month to do if it doesn't meet the requirement, with 1 month to fix those things. So it takes a lot of time and do a lot of things, not just a pre-place cell and reroute. So this one is like the simple way. No, it's not even simple. It's like it's not that. It's not that. It's a lot of things I cannot explain here because that like that kind of like everything. So I think with that we have we finished this part, but we will we take all right, we get 5 minutes. We take 5 minutes break, and then we'll go to this. I think this one. Yeah, here. How logic synthesis works. What does synthesis really? What logic synthesis really does? So we take 5 minutes. We will go back at 8:30. Okay, and then we'll I will make it quickly to go through this one so that you have an idea about how the synthesis works. And this one is I summarize the paper from Devadas, and also I add some more with the my own work at the time, which is now is very a simple one. It looks very simple. At the time it's different. Okay, so we take a 5 minutes break. Yeah. I think I need to go fast this so that we can go to the portion that it might have the question. So let's see. Yeah. So what does the logic synthesis do? So it will from the RTL to the get netlist ready for PNR. That's first thing. So inside the logic synthesis, there will be the you have the two-level minimization, two-level logic. It means the sum of products, right? So you have a sum products. Let's say like A, B, C plus a D, E, F, and so on. That's a two-level means like this: A, B, C plus E, D, F. You have like this one is a plan or like sum, and this plan is the plan product, right? Product term. So that's why called like a two-level logic. Multiple level. So when you have like another one here from 3 and up, you have like a multiple level logic optimization. Digital logic is composed of data path and control logic. Right? Data path is a mix of using the macro and IP. IP is the intellectual property, which is whatever like you design a block, and then you just make it a hard like a black box and you sell it, and that called like the intellectual property. So the data part, let's say that you make like a very like a fancy fast multiplexer, and you claim that like they do that like a multiplexer with the speed like the delay usually is 100 picosecond. You make it only like 50 picosecond. Then you just like box it, and then like make the like the information about the day and the timing, about the power, about area, and then the pin, and then whatever the information needed for people to use, then that one will become IP. Macro is the same, but the macro is a one like a I think I explained that before already. Control logic and the data part has the macro and IP, as also has also the standard cells, which is the gate, like the nano and so on. So with that, they can use only like the mix between using macro or they use a logic synthesis to synthesize the data part. The control logic usually, because control logic it means a very random, so there's no way that there will be some macro to do that, because every chip will have a different kind of control, right? Every like when you will turn on here, turn on that, turn off here, and where something, the purpose will be different from chip to chip, from like a vendor to vendor. It's like nothing is a resemble, nothing is the same. So which is that because of it, you cannot standardize it. When you cannot standardize it, you cannot make an IP or macro to be used over and over again. Then logic synthesis is the tool to synthesize it. ROBDD, technology mapping, those FSM, those things we will explain. Those things will be introduced in the logic synthesis. So here the logic synthesis, the first work of logic synthesis is to convert the RTL code into a Boolean system. Then from there, the Boolean system, which is you have A or B or C and whatever, so quite like that. Then you will like have the how to so you have to like convert that. From there you have to convert that in some kind of data structure so that you can optimize the system, right? So the data structure used to present the Boolean system is like the sum of product, right? No matter what, you have a system is like a very complicated, but you can like in theory you can push it down, you can collapse everything, and finally it will become a sum of product. Very costly, because when you push it down, you just like you just collapse everything, you have like a big sum of a big product, right? That one, it looks like it's not optimum, but in the old days you have the POA. I think I'll talk about that later. The second data structure is a BDD, ROBDD, AIG, and the final one is a Boolean network. You read the 3 last line. I think the Shannon expansion is an easy one. I think you guys know it in the information theory. Now, what is a BDD? The BDD is a present as a way like you have a binary decision, right? Diagram, which is, let's say you have a 0, 1, 0 here, which is go like this. It starts with some variable, like let's say x1, and then on the left, the variable take the value 0. On the right, it take value 1. So that means that you have the straight line is a 1 value, and the dotted line is corresponding to the 0 value. So with that, you have a x1 with 0, 1, 0. You have a x1 take 0, right? And then you have here x2 take 1, and then x3 take 0. Then the value it should be 0 here, and so forth. You just keep going. That's the way that they and then like they build that based on the Shannon expansion. Our BDD is just a BDD, but with an order BDD and reduce. Order means you have the order of the variable. When you do the decomposition with the Shannon, you use the same order, right? You go from this, you have x1, x2, x3. You go this branch, it's still the same. If you go like that again, let's say you don't have it. In another one, let's say like up here, like you have this one is a x0. You add it, it will is 1 here again, and it will follow the same order. It's 0, 1, 2, 3, the same order. That's called order BDD. Now reduce. The reduce is like a reduce so that like you have from the big one like that, so it's reduced to like that. Reduce as like only like you have how many? 1, 2, 3, 4, 5, 6, 7, and then 4, 6, 8. 8 plus 7 is 15 nodes in total. This one you have 1, 2, 3, 4, 5, 6. So that's why that's called like you reduce the number of nodes so that you have only 6. If you have that smaller 6 like that, it also means you have a small area. So it's implied that ROBDD is the best for the area optimization, right? AIG is the AND inverter graph. So to present that, okay, I think this one is easy. Boolean network is another way that its node is a function. Its node is a function, and you just like replace that. You have a G file here, and you can look at that and you can understand. I want to go like a BDD versus a Boolean network. This one, I think you read that as like okay, read that, and then if you have question, ask me. But this one is not okay. It's not like you can ignore this one. That's fine. Two level, it can be ignored. Yeah, this one can be ignored. That's fine. Two level logic optimization. So as I said, two level, which means you have a SOP here, and here's the POS, the product of sum, right? So the POS, the product of sum, can be implemented through the SOP using the De Morgan law, right? De Morgan law, you just like do like you like do two not at the same time, and finally you have like this one is the POS. Why two-level logic optimization? Because in the old day they have the programmable logic array. It used this. So this plan is the AND plan, and this plan is the OR plan. So you have that like in here, right? So you can see that A, B, C, F, G here, right? So the first thing you have yeah. So F, take it. Okay, I think. So you see that F is here. F is like the sum of these two products. This product is like here and here, right? So if you write it down, I see like this first product is come from A, right? Yeah. And the second product is, sorry, A, and then this one is come from C bar. Hold on. The first one come here. I think it's not A. It's A. It's not A bar. Yeah. The first one is A here, come here. So this one is A. And the second, and then like you have this one come from here. Oh, sorry. I think it's correct. Just do that. Okay, it go from, I take this one first. This one first. So it go here. You have an A, come here. This one's the A bar. And you all go from like this one coming here. You have this one is a B bar. Right? So that means that the first product term will be A bar, B bar. Go in here. The second product is this one. So you go in here, you have A bar, inverse one more, and so this one's the A. And then the next one is a C here, C bar, right? So the second product term is a AC bar. That's why you have a one here, and then these two come out with the product term. With that, you can have a G, you can arrive your G. It's like that. G here is like only one here. See? It's only connect here. So this one is called out here. So it's only A bar, B bar. Because here there's a no connection. All right. So this is the two level and the multi-level. You see that. Now you have a F, A plus B plus C multiplied by C, by D. So you have this instead of only like a A, B, C plus D, E, F. Now you have a factorization here, right? This one you have a factorization. Whenever you have factorization, then you have a multiple level logic. Now the mapping. So the mapping is what when you have this one is the Boolean system. Whatever you represent that. Now you need to map it. You need to map it into the cell. This one is a list of cell provided by the cell library, right? And then this one is symbol, and this one is the pattern or DAG. So you look at the DAG, pattern DAG, so that you can map into, right? So for example, there's only one rule for that. The cover for that, like the input of one pattern must be the output of some other pattern. So this one, okay, this one is illegal because the output here, right, is correct, but this node go into this one. This node is not the output of anything, so that's why it's illegal. That's why I think this one is illegal because of the input, right? You have this one go. Every input is from the output of another pattern, and that's how it maps. And then like in the algorithm is like this. It will go into the graph. It will pick one. It will combine with another one, and it will just go to find the cell on the left. It match. It mark it. It keep going until it match it match the next one. So and it will find. It depends on the criteria of area or performance. They will map in a way that meet that criteria. So here, I think it's an easy way to, you see that this is the second part here, right? This one is an easy way to demonstrate how it maps. But for sure, I think in the real life, it's very complicated, but that's a way to. And there's also like a lot of other ways to do. This one is a Boolean collapse. So for example, when the reason we collapse means like you replace the subfunction by its description, which is in this case you have this one. You have SF1 and SF2, right? So you can see that like if you collapse total, right, you replace every SF1 by its description and SF2 by its description. So first of all, I collapse the SF2, which is SF1 now. SF1 is the function of B, C, and SF2. SF2 is a DE. I replace this one of SF2 by this, and we write this whole thing here for that. Then I have this one. Why do I do that? I do that because I think that like okay, the guys before me or whoever did that, I think that is not. I'm not sure if it's correct or like no, not that. I'm not sure that if it's good for the performance, because you see that It can be like a 1, 2, 3, right? When you put that, you have a 3. If I can find a way to like represent this one in only like a 2 level, I will have a better performance. So the Boolean collapse total here, in case that like the Boolean collapse and the total collapse here, it means that you don't have any subfunction in the network, right? It's here you have that no subfunction. The reason for that is that you think that you can do a better work. Why or whatever, that's another thing based on a certain criteria. Maybe the old thing here is good for some purpose, but now you reuse that, you map into a new one, right? Your purpose is different, your target is different, so you have to collapse it to do your way. That's why you like collapse it totally. There's also like a partial collapse, which is, for example, like collapse only the non-share subfunction. The non-share, for example, here you have SF1, right? SF1 is going here. The SF1 here is only going here. It's not shared by anything else. But the SF2 is going here first. And going here too. So it is shared. So that means that SF1 is kind of look like a doesn't help here. So I just collapse the SF1. I keep only SF2. So you see that the final one will have only one SF, which is SF2, for example. Technology mapping, I think this, yeah, okay. So basically you have an area two mapping. One is area oriented mapping using ROBDD. As I said, ROBDD will give you like compact graph, so it's good for the minimization of the number of nodes, which is a minimization of the area. The speed-oriented mapping will target the depth of the Boolean network, sacrificing the area or like the number of nodes, right? So the thing with the depth of the lot, okay, there's a thing like this. Sometimes you reduce the node, the depth of the logic node, the depth of the system, and later on you will like M2, you will do the delay reduction, because when you have like the number of node is reduced, the second step you will like let's say you have the NAND and you want that to be fast, then you use the fast NAND instead of the slow NAND, right? With that you combine like reduce the depth and reduce the delay, you have a better performance. Sometimes you do that like but usually you have to do like reduce the depth first and then reduce the delay later, because reduce the depth so that you know where you should reduce the delay. And we can like usually area mapping will lead to the small area. So when it's a small, then the distance between the cell will be smaller, right? Shorter. When it's a shorter, then you have like a shorter white length. So it some kind of improve the white delay. So which means like when we want to have a high performance, it's not only like we use only speed mapping, but we need to combine with first area mapping and then we do the speed mapping. That's like how and then we combine that so that like first of all you reduce the area and then you do the speed mapping. You don't do only speed mapping, because you do speed mapping, the area will be exploded, then you have a more wide delay, and even you reduce the depth but you still have the wide delay, it will like cancel out your optimization of the cell. And critical area optimization, this portion is like this. The network will be like this, right? Let me the network like this. So which is I think in terms of logic depth, right? So this one is a critical because it's like let's say like you have a 20 level. This one you have only 5 level, right? 20 20 logic gate. That means a 20 level. Now you look at that. So if you want to like it's no point, right? It's pointless to optimize this one, this area, because it's already fine. So it's already like a short and fast. So you don't need to do the speed mapping for this one. Only you do this one. This called critical area optimization. You just like detect, determine, and then like extract the critical area, and then you optimize this one only. Or because this one, I think there's another one like this here too, right? And this one, you see, this one and this one is share, right? So because it's share, when you do like the optimization only one like this, then this portion will impact the other, right? And maybe this version will be like it maybe make this one is longer for some reason, because it's like on the way here it's fast for this one, but for this one it go from here, right? And it go out here. It can be like a longer. So which is usually we do like we optimize the critical area, but we usually we put like this. We have this one, we say that like a near critical area. So we optimize not only this critical, but we also optimize the near critical one. So this one didn't present here, but I just explained here. All right. So with that, I think we conclude the chapter. Okay. So this one is a trend. I explained to you a little bit that you have the keyword you can search for that, but if you have it, this one won't be like us. That's fine. So if you are curious, I can explain to you like offline, not offline, because just send me email or like you ask, I will explain. But with this, I think again the question will be easy again, and then you just like this, right? Like this extra slide, you need to learn, you need to read that, and if you don't understand, you have to ask along with the main slide from I think the main slide that like chapter 1, 3 and so on, along with this one. That's all I need you to read. All the other material is not needed. So if you have a question, you can ask. If not, I think just wait until next week on Thursday. On Thursday, you can ask me like whatever. Just put that together, and on Thursday, you can ask me on that before the midterm test. Today, I think I go a little bit fast because I didn't realize that there's too many things to cover. I thought that we have enough time, but that's okay. All right. So, any question? Page 78. What can we do in page 78? Okay, hold on. Let me. Okay. You mean this one, right? Okay. What can we do in rewrite the code? Oh, for example, let's say like when you let's say you write the code, and then we implement that, we do the synthesis, and it didn't meet the timing, and then we see that like okay, the timing part is like the depth, the logic depth is about 20 level, right? That means that when we say the logic depth is 20 level, it means that there will be 20 cells along the way, right, along the path. Now when you go back, you have to see like your code writing those things. If it's like you have to change so that like you can imagine like the code, what is the impact of the code to be like what is the code to be compiled into the logic gate, and you have to change it, which is it's not easy to do. But if you write that like somehow like you have to go like describe that in like the structured way, the structural style, which is like you describe that in the structural style, which is using the cells directly, or you can like change your in the blocking non blocking thing. You can try to blocking or non-blocking assignment, right? So usually with the blocking or non-blocking, it's like with the you use non-blocking. Usually it's with the flop. You use with the flop, it will cut the timing part. It's a split the timing part. You have a shorter, but the problem with that is it's a shorter, but then it will be like a more flop. The rule of thumb is that if you have a more flop, then the frequency will be higher. But it's also like the area will be higher too, because the flip flop is you one flip flop you see how many at least is 1 2 3 4. The area is bigger than like the regular one. So if you have that, and also flop because you have the clock coming in, usually it consumes a lot of power, right? So that's why I think we like you can see that like usually in a high performance CPU or high performance processor, the part is very short, so that like the performance will be high. So you said like what can we do to in the rewriting is a very big question. It depends on, but the thing is you need to look at the part cause the trouble in the implementation, and then you relate that to your code, and then you verify the code that related to the failure. No, when we have the question is when we have a multi-level logic expression, do we always have to optimize that to a two-level logic? We don't need to. The two-level logic is like we just like do that two-level is for the old day when they have the POA, which is only two-level, like a two plan and all, right? So they down to that and they minimize that. That's the old days, which is like I present that to you kind of like a history. But nowadays there's a no such like not no such for the simple application. They still use that POA. But the short answer is no. We don't need to. We don't need and we don't have to optimize down to the two-level logic. Why? Because it's not efficient. When you have a multi-level, it means that you have some kind of factorization, which is it reduce the number of nodes, which is like already like some kind of optimized, right? So the thing I said like when we collapse it totally, it's just like totally for some like a critical part. Because in the design, right, you have a multiple output. Each output is a one function, and the output and the function can share, right? So which is like if you want like some output very critical, they can collapse totally. But when they collapse totally, the purpose is like so that they can like refactorize that again, so that they have a better performance. You're welcome. All right. So I think I didn't have time to explain to you about like a factorization. It's just a simple like explain like what is a factorization. But factorization is the big field, not big field, but like there's a lot of algorithm to do the factorization. Then when you factorize that, you will have to do the optimization of that factorization. Then after the Boolean network, the Boolean system is optimized, you start to do the mapping. The mapping means the input is the optimized Boolean network, right? The output is the get netlist. That means the first step of the logic synthesis. Any other question? Okay. So, Professor Ten, you have anything else to like let the student know? If not, I think you will inform the class of the Thursday, right? To for the new information. Like
Yes,
yeah. I think they will have the test together with the. So the CC1 is the class of Thursday, right?
yes,
And CC2 is the class of Saturday.
Saturday. Yes.
Yeah. Okay. All right.
Okay. Goodbye.
Oh, okay. Another one in BSI, is that something like a mass pouring to protect signal Y, like in PCB? You mean the shielding? Mass pouring. I don't know that terminology. Could you explain more about the terminology you use? What is a mass pouring?
Dạ, kiểu ở trong vẽ PCB á thầy, thì
Mm-hmm.
để chống nhiễu mấy cái dây signal á thì mình đổ
À,
đồng.
nó có cái shield, yeah. Cái probe gì?
Dạ, đổ lớp đồng ground ở xung quanh mấy cái tín hiệu á thầy. Mình phủ lớp
Oh,
đồng.
no, đâu có đổ được, cho shield thôi chứ. Ở PCB nó chỉ shield hai bên thôi chứ làm sao mà đổ phía trên được, right? No, I think even PCB. Okay, the way that to chống nhiễu á, to like prevent the noise. So in the VSI they have the same thing. That's why it's called shielding. So the shielding is like you have the signal go right. It's just like go forward, and then like along the way they will have a two straight wire go in parallel, and those wire will be connected to the ground, so that to prevent the noise, because it's everything is on the surface, right? So like this, and then like and on top of it they will have a plan. On top of each chip they will have the on the ground. Okay, on the bottom they have the ground plan already, so it like that prevent the news from that. On the top they have a power grid. It's also like to prevent. So that means that the top and the bottom there's a protection against the noise. That noise that come from outside, like from the lining in the atmosphere, the lining, or like you have when you turn on the light, there is a spark, right? There's a spark, electric spark. That one is noise, but those noise would be like eliminated with the top and down. Now the noise we talk about here is noise inside the chip by itself, which is come from like the it comes from like the inside the chip. So which is the same surface. That's why they just need to do like a 2Y in parallel of that. So that's called the shield. And I think you said that like they pour the copper on top of the wire in the PCB. I never see that. Do you know that?
No, they just pour the copper around the signal wire to
Then
protect.
nếu mà làm mà bỏ cái copper mà on top of the wire thì nó touch, làm sao nó cắt ly với cái insulate with the copper wire.
Dạ, nó không có đổ ở trên mà nó đổ xung quanh đó thầy.
Thì đó,
nó
đúng
đổ.
rồi, là shield đó. Yeah.
Dạ.
Nhưng mà I think it's okay. What is the frequency of that you have to do? Frequency of the signal.
Khoảng 300 MHz thì sao thầy?
Oh, 300 MHz. Yeah. And then you have to do it. Yep, you have to do it. But it depends on like 300 MHz with the PCB. Yeah, you have to do it. But let me see. Yeah, you have to do it. But inside, I think 300 MHz inside the VSI is like a slow frequency. It's a low frequency, not high. But because PCB, you see the PCB, first of all, everything is like you have the copper is in the distance is about like a centimeter, right? So that's why But if they have to shield it, still I think surprised me, because maybe the quality of the PCB is not that good, because you can see that in the you see in the PCB board of Apple or the cell phone something, they don't have the shielding like that, because they have a good quality of PCB and good quality of those wire running, right? Because the PCB good quality, that means like a good insulation. So they have a much less the noise, and then usually they don't have the buzz going around in the PCB. Anyway, if you have to do that, I think it's really like anyway, okay. So inside when you have that, and usually not usually, most of the time, the signal doesn't need the shield. Only the clock need the shield, because the signal in that when they have when the signal run in parallel, usually it doesn't happen often that the signal run in parallel for a long while. It just run in parallel for maybe like 20, 30, even like up to 100 micron. With that, it causes the crosstalk. However, those crosstalks, it doesn't like not enough to cause a trouble, but just like a mild trouble. When they have it, they will try to like for the signal, they will try to reroute it. So instead of like do that way, they reroute it, then they won't be in parallel anymore. But the answer for now I got it. The answer for the signal wire in VLSI, we don't do the shield for the signal. We only shield for the clock, because I said clock is crucial, right? It's the heart of the chip. So we have to protect the clock integrity, signal integrity to the maximum. So that's why for the clock, we have to shield that from like the root down to like a kind of like almost like more than half of the clock. We have to shield it. But the signal, we don't. All right. Okay, you're welcome. Yeah, I think a little bit more is there's like in a small chip there's about like about 500,000 to 1 million NAS at least. With that million NAS, right? Imagine you have a million NAS. You cannot shield it. No way to shield it. And when you want to shield it, it's not easy because it's compact, it's dense. So you want to shield it, then you will have like, because it's route already, and then when we see, oh, this is a signal is critical, you want to shield it, then it will impact the other route and it causes more trouble. So the better way is just to reroute that, go different way, so that like you don't have the noise anymore. All right, we done here.
Okay, thank you.
Yeah. Okay, thank you, professors, and everybody. We see you in on Thursday next week, and then prepare your question, and then I think we can like see you next week.
Yeah, see you.
Okay, bye.
Bye.